So when we analyze our data, we want to be able to see how the average changes over time and how the variation changes over time. So that means we can't look at the data as one whole. Instead, what we're going to do is we're going to divide it into groups. And we're going to look at the mean and the variance within each of those groups and see how those things change over time. So it turns out that how we group things matters a lot. And so in this section of videos, you'll see that there are some extra videos that are specifically focused on how do we define the groups in ways that make the conclusions that we draw statistically valid. In particular, we're going to try to set those groups up in ways that we can see that we can focus on where there might be discontinuities in the data. Because what we would like to do is we would like to group things together so that we minimize the in-group variance, so we're grouping things that are similar, and we maximize the between-group variance, which means the places where we think one group is likely to be different from another group are good places to divide the data. The first thing we want to verify is that the range is in control, because if the variance is not in control, looking at the mean isn't going to make any sense. So if you think about the distribution of a range, we know that it is not a symmetric distribution because the tails can't go the same distance in both directions. In particular, a range can never be negative, so the range is not normally distributed. So we're going to set the action limits so that 0.1% of the population is outside of the action limits, and the warning limits so 2.5% of the population is outside of the warning limits. So the calculation of the action and warning limits on the range chart are just multipliers times the average range. And the multiplier that you choose depends on how many things are in your sample. So n is the number of things in a group. So I have here, as an example, some data. You can see in column 2, we've gathered some statistic every hour for a while, and it doesn't really matter what it is. It could be the width of a widget, it could be the rate at which we do things. It doesn't really matter. But we've gathered all of the data, and then I have used the offset function of Excel to group that data into 8-hour shifts. For each shift, I have calculated the range of that shift. And then at the bottom, I have the average range is almost 14. So for n equals 8, the multipliers that the range chart require are here, and that gives me range limits. 4 is the lower action limit, 7 is the lower warning limit, 22.7 is the upper warning limit, and 28.5 is the upper action limit. And then I've had it calculate, is this range below the lower action limit? Or is it below the lower warning limit and not the lower action limit? So is it in each of the 4 ranges that we're worried about? And you can see there are a couple of times where I have crossed the warning limit, but nothing that has put me outside of the action limit, so I'm really not concerned. And if you look, you can see those are the 2 points that it was a little worried about, but they're still just in the warning area. So I would say we'll come up with more complete rules for what is in control, but this looks pretty in control to me. So when we're calculating the chart to see if the means are in control, we're going to assume that the means come from a symmetric distribution that is unimodal, which means it has one peak. And if the process is stable, then we would expect most of the individual results to be within the average observation plus or minus 3 sigma. because we are looking at averages of groups, we can make a slightly tighter range for those sample means. We can say that a sample mean is likely to be within the grand average of the sample means, plus or minus 3 standard errors, where standard error is sigma over the square root of n. So we're going to make the warning limits be 2 standard errors away, and the upper limits be, or the action limits be 3 standard errors away. And you'll notice that this picture is not drawn to scale because the distance between the process mean and the lower warning limit should be twice as big as the distance between the lower warning limit and the lower action limit. So the warning and action limits on a mean chart are centered around x double bar, which is the grand average, which is the average of all of the sample averages. For the action limits, we add or subtract 3 times the standard error, which is sigma over the square root of n. And for the warning limits, we add or subtract 2 times the standard error. If our sample size is relatively small, then the standard deviation of a sample is not a very good estimator for sigma. So when our sample size is small, instead of standard deviation, we're going to use range divided by Hartley's constant. And Hartley's constant depends on the sample size. Now, since Hartley's constant and the square root of n both depend on n, we can turn all of the multiplier into one constant, which is called a2, and just add or subtract a2 times the average range. So if I go back to this example that I showed you before, I've calculated in this column the average for each one of the samples. And that has allowed me to calculate the grand average, x double bar, which is the average of all of the sample averages. And then over here, for n equal to 8, a2 is 0.037. So I've calculated my lower action line, my lower warning line, my upper warning line, and my upper action line. And like I did for the ranges, I made it calculate whether or not we had crossed any of those lines. We've crossed one warning limit, but not any of the action limits. So that looks pretty much in control. And if you look at the chart, nothing seems that out of the ordinary. This is the one point that was beyond the warning limit, but things look reasonably in control. So you'll notice in my example that there were things that were outside the warning limits, and I didn't overreact to them. It turns out that if we build the limits this way, then there is a 1 in 40 chance that something will be in zone 2, which means it's a warning but not an action. So that will happen sometimes. And in fact, there's even a 1 in 1,000 chance that while we are in control, something will be outside of the action limits. If you have gathered 1,000 samples and you see one outside, I wouldn't get too worried. But that gives you some idea of how often you should expect to see things in those warning and action zones.